So the first few days, you have been reviewing kinematics, which is just describing how something is moving. Now we're moving into dynamics and reviewing concepts such as forces and Newton's laws. So forces are what cause objects to move the way that they move. They're generally described as pushes and pulls. So if you push an object, maybe it moves, maybe you make it speed up, or maybe it just goes at a constant speed. But you push things or you pull things, and that's why they move the way that they do. So we'll be reviewing that. So first slide, what is a force? It's a push or a pull, as I said. It influences the motion of an object. It's a vector quantity. The symbol will be a capital F with the harpoon. And the units of force, the standard units are newtons, after the physicist Isaac Newton. What are some types of forces that you know of? So forces you heard of in grade 11 and maybe worked with. So you should have talked about gravity last year. That's a force of objects pulling on each other due to their mass. More commonly, we use Earth pulling down on us or on objects, keeping them on the ground. Other forces you might have heard of are friction. So we'll work with that again. That happens when you have objects rubbing against each other. They apply a force on each other. You may have heard of tension, which is a force, the word we use for a force of a rope or chain or something like that, pulling on an object. Normal force should have been, it's an important force that you should have talked about. That's the force of when two objects are pressed against each other, like two surfaces or a surface pressing on an object. It's the force applied from a surface. And the direction of that force is always at a 90-degree angle to the surface. So, for example, if you're just standing on the ground is actually pushing upwards on you, and that's called the normal force. And the direction of that force is perpendicular to the floor that you're standing on. However, if you're standing on a ramp, let's say, okay, you are on a ramp now, you have a normal force acting on you, but now the normal force is actually angled. It is pushing you at an angle that's 90 degrees to the ramp. Okay, so that is the normal force. Furthermore, if you are leaning against a wall, okay, so now we'll just be leaning against a wall here. Now you actually have two normal forces against you. You actually have the wall that's providing normal force pushing you outwards or to the right in this diagram. But you have a second normal force pushing upwards where your feet are. Okay, so these normal forces are forces that surfaces are pushing you at, and they're always at a 90-degree angle to whatever the surface is. Other forces you may have heard of in the past, electric forces in grade 9 when we talked about electricity. So like charges repel, unlike charges attract. Those are called electric forces. Similar to electric forces, we have magnetic forces. So if you played with magnets before, you may know that they can push and pull on each other. So there's forces there as well. And I could list a bunch more, but we do have kind of a general term for a force. If you need a general word for a force, you don't quite know what to call it, like it's not one of the ones listed above, then you can just use the general term applied force. Okay, so an applied force, maybe like literally if you push a box, it's you pushing on the box, we're not going to call that gravity, friction, tension, normal, electric, or magnetic. We're not calling it any of those things. You physically pushing on a box. We would just call that an applied force in that case. All right, so going back to newtons, forces are measured in these units called newtons. And to try to give you an idea of how strong a newton is, there is this relationship here. 1 Newton. How strong of a force really is 1 Newton? Well, 1 Newton is capable of causing a 1 kilogram object to accelerate at 1 meter per second squared. Okay, so that may or may not be helpful as a visual, but 1 Newton is capable of causing a 1 kilogram object to accelerate at 1 meter per second squared. 9.8 newtons, or close to 10 newtons, okay, approximately 10 newtons is the force needed to hold up a 1 kilogram object. Okay, so if you were to find a 1 kilogram object and just hold it in your hand and just keep it in midair, you have to apply approximately 10 newtons to do that. It's really like 9.8, but it's pretty close to 10 newtons. So that gives a general idea of how strong a newton is. 100 newtons then. If you apply 100 newtons of force, you can hold up a 10 kilogram object. So if you lift weights, I think a lot of I don't know actually. I think no, 1 plate would be 20 kilograms. So half a plate, when you're putting on a barbell, would require about 100 newtons. A full plate would require 200 newtons. Okay, free body diagrams and net force. So a free body diagram is a diagram that shows all the forces acting on an object. There are rules, a certain set of rules that I prefer when drawing free body diagrams. So I want the object to be drawn as either a box, a circle, or a dot. I don't want you to get fancy and draw an actual piece of art that represents the actual object. I just want you to use a simple shape, either a box, a circle, or a dot, to represent whatever the object is. And then you have to think about every single force that's acting on the object and draw an arrow for each of those forces. The arrows need to point in the same direction that the force is pointing at. And I would like the relative lengths of the arrows to be approximately accurate, approximately to scale. I don't need you to use a ruler to make it perfectly to scale, but they should be somewhat approximately accurate. And furthermore, every force needs to be labeled. Every force needs to be labeled, and I have decided on a certain set of subscripts for specific forces. So the force of gravity, I'd like you to use a subscript of G, as shown in this example on the right. For the normal force, I'd like you to use a subscript of N. For friction, I'd like you to use a subscript of lowercase f. And for applied force, I'd like you to use a subscript of A. There's no tension in this example, but if you had tension, I'd like you to use a subscript of T. Okay, so those are the general subscripts you can use to distinguish the different forces. So we're going to do one example here. Well, actually, the example is already done. Draw a free body diagram for a book being pushed to the right across a table so it accelerates. So yeah, that's this example that's drawn right there. The box represents a book, so that's the object. And then if I'm pushing that across the table to the right, I'll have an applied force that needs to be pointed towards the right. So that's why I have my applied force here. The book is on a table. So the table is providing an upwards normal force for the book. Actually, I'll draw my artistic diagram here. So I got my book on a table, and I'm pushing it to the right. So the table, it's on a table, so the table is applying the normal force. And that normal force, as I said earlier, has to be 90 degrees to the tabletop. So it points upwards. Then there's gravity, because the earth is pulling down on this book. So I've got gravity aiming down. Gravity is basically always going to be aiming straight down for any of these examples that are just objects on the earth. And then there will be friction. As I slide the book across the table, there's going to be friction resisting that. So I drew that in the left direction. Now, the book has to be accelerating. It has to be speeding up. And we're going to be getting into Newton's laws later in this video, but according to Newton's laws, if you remember them, in order for an object to be accelerating, the forces should be unbalanced. You need one force to kind of win, I guess I'll describe it as. So in this case, I've got the applied force. I drew it longer, okay? I clearly drew the applied force longer than I drew the friction. So the applied force wins, and that's going to cause the book to accelerate and speed up. In terms of gravity and normal, the book is not moving up or down, so they need to actually be equal in size to cancel each other out. So I drew them the exact same size, and to help out the reader, to tell them that you meant to draw them the same size, I put these little tick marks. Okay, if I put an identical tick mark on two different arrows, I'm trying to communicate that they are the same size. All right, net force. Net force is defined as the sum of all the forces acting on an object. You combine all the forces together, what's left over, we call that the net force. Sometimes I'll use the words overall force or even the word resultant force. They all stand for the result after you add all the forces together. The symbol for net force is F with a harpoon and the subscript of net. So we'll try to calculate the net force in these examples. A. So I have two forces acting on an object, 100 newtons to the right and 150 newtons to the left. So just adding those two together, they're in directly opposite directions to each other. So the net force, I asked which one's bigger, that one wins. So sorry, I'm just writing this general statement out here. The net force is adding these two together. So it's 100 newtons right plus 150 newtons left. And when you add those together, the left force wins by 50. And so the overall is going to be 50 newtons to the left. All right. B. We have 600 newtons up is one force. Then we have the net force is 200 newtons down, and we have to determine the second force. Okay, we have to determine the second force. So this is, you have to think a little bit different here. So I'll have a free body diagram. It's saying that we have a force that's 600 newtons up, so F1 is 600 newtons up. Now we need to find out what the second force is so that the net force makes 200 newtons down. So I need a downwards force. It's got to be essentially like how long does this have to be? That's the question. And if my overall total has to be down, then my downwards force has to win. It has to be bigger than the upwards force. And it has to win by 200. So just doing some mental math, that's going to be 800 newtons down. Okay, so that will solve the problem there. What is the net force on an object remaining at rest? If an object is not moving at all, one of Newton's laws says that the net force will have to be 0. Okay, everything has to be perfectly balanced. There could be no leftover force. Otherwise, the object will not stay at rest anymore. And D, what is the net force on an object moving at a constant velocity? So this may not be as intuitive as part C, but if you learned the Newton's laws properly last year, the answer to this is actually also 0 newtons. But you might think, oh, well, the object is moving, so there has to be a force acting on it. That's actually not true. An object can be moving with no forces acting on it. So I want you to think of outer space. You think of outer space, and you have an asteroid just moving through outer space. And we'll just say that this asteroid is not anywhere near any kind of planets or solar systems at all. It's just in deep, deep space with nothing else near it, so there's no gravity influencing it. This asteroid is just going to keep moving. It's actually going to keep moving at a constant velocity. There's nothing that's going to affect it. So it'll just keep going in this straight line until it eventually gets close to something else that's going to affect it. But while it's moving just in deep space all by itself, there's nothing pushing it, there's nothing pulling it. There's actually 0 newtons of forces acting on it, and yet it's still moving. Okay, so it is possible for an object to move, even if there are no forces acting on it. This is actually a really important, it's a really important concept to understand, that if something is moving at a constant velocity, then the net force is equal to 0. Okay, it's one of Newton's main laws. So here are the 3 laws. In the first column, I wrote down how textbooks will generally describe these. But on the right-hand side, I wrote down simpler ways. At least in my mind, there are simpler ways to understand Newton's laws. So Newton's first law says, an object at rest remains at rest, and an object in motion maintains its velocity in a straight line unless acted on by an unbalanced external net force. So that was parts C and D from the last slide. I was trying to say that 0 newtons of net force will mean an object is just going to keep doing what it's doing. So if it's at rest, it will stay at rest. But if it's moving, it'll just keep moving like that asteroid at a constant velocity. So my simpler way of saying that is that if the forces are balanced, in other words, if the net force is 0, then the object will not accelerate. Okay, balanced forces, or a net force of 0, means there will be no acceleration. It could be moving, it could be at rest, but it's not accelerating. It's not speeding up, it's not slowing down, and it's not changing direction. If you want an object to accelerate, then you need to have an unbalanced net force. Like, you have to have a non-zero net force if you want to make an object accelerate. If you want to make it speed up, you have to unbalance the forces. If you want to make it slow down, you have to unbalance the forces. Or if you want to make it change direction, you have to unbalance the forces. Okay, so that is how I understand Newton's first law, and that's how I suggest you understand Newton's first law, is that these two, it's really two concepts. They're related to each other, but you have to think about them in two different situations, possibly. Okay, so that's the first law. The first law is very conceptual. The second law is more mathematical. The second law says the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. The direction of the acceleration is the same as the direction of the net force acting on the object. So all of those words can be summarized in one nice formula, which I wrote on the slide here. The acceleration of an object, so A, will equal the net force on the object divided by the object's mass. This formula only works if the units are consistent with each other. And the SI units are written on the right here. The standard units for this formula are acceleration should be in meters per second squared, the forces should be in newtons, and the mass should be in kilograms. So you may have to do a unit conversion before using this formula to make sure you're in the SI units. So this is saying that for an accelerating object, the stronger the force, the higher the acceleration is going to be. Net force, I mean. The stronger the net force, the higher the acceleration is going to be. And I think that makes intuitive sense. You push something harder, it will accelerate faster. And similarly, I think it's kind of intuitive that the heavier an object is, the less it's going to accelerate. Okay, so you're pushing something really, really massive, you're not going to be able to accelerate it as much as pushing a light object. So we have mass in the denominator, okay, because we're dividing by mass. So the heavier the mass will be, the smaller the acceleration is going to get. That's essentially what the words directly proportional and inversely proportional mean. So like the net force is in the numerator and the mass is in the denominator when you're equating it to the acceleration. A lot of the time, you will see this formula instead. It's the exact same formula, just both sides were multiplied by mass. Right? So these are the same, they're not different formulas. So you can use whichever one you are more comfortable using. Some people, I guess, don't like to write fractions, so they choose F equals ma as their starting formula. But it is entirely up to you. All right, Newton's third law. Whenever one object exerts a force on a second object, the second object exerts an equal force in the opposite direction on the first. So forces come in pairs. That's one important concept that the third law is saying. Forces come in pairs. Every time one force is applied, there has to be a second force that's acting back on the original object in the opposite direction. So I've summarized that with this statement down on the right-hand column. I said the force of object A pushing or pulling on object B will equal to the negative of the force of object B acting on object A. So they are equal in magnitude, so an equal number, but opposite in direction, and that's why there's a negative sign there. They're equal in size, but opposite in direction. So the example here, A, B, C, and D, I believe we'll go through all parts of Newton's second law, or Newton's three laws. Rayshawn, a 90-kilogram person, is standing next to Iverson, who is 60 kilograms, on a frictionless surface. We're simplifying the situation by making it frictionless. Rayshawn pushes Iverson, causing Iverson to accelerate at 6 meters per second squared east. With what force did Rayshon push Iverson? So that can be solved with Newton's second law, F equals ma. And we're talking about Iverson's acceleration. So I'll circle them in the same color here. Iverson is the one who accelerates at 6 meters per second squared. So in the formula, we're going to plug in Iverson's mass, 60 kilograms, not Rayshon's mass. So it becomes 60 kilograms times 6.0 meters per second squared. That makes 360. This should be the two significant digits, so I'll just underline the first two digits. The units of force are newtons, and the direction here is east, according to what the question says. Okay, so that is the force that Rayshon pushes Iverson with, 360 newtons. B, what reaction force does Rayshon receive? So part B is referring to Newton's third law. So part A, we use the second law, and we discovered that Rayshon pushes Iverson with 360 newtons. Well, Newton's third law says that Iverson actually must push back on Rayshon with this exact same magnitude of the force, just in opposite direction. So I would simply say it's 360 newtons west, okay, opposite direction. So that is Newton's third law. Sometimes you'll see me write N3 to refer to Newton's third law. And sometimes I'll write N2 like to refer to Newton's second law. Just a short form. Okay, C. What will Rayshon's acceleration be during the push? So Rayshon pushes Iverson, so Iverson moves, but Rayshon's actually also going to move because of the reaction force. Another example of reaction force is recoil from firing, let's say, a shotgun. If you fire a shotgun, you shoot a shell out really fast in one direction, but that will actually cause the gun to move backwards, and it might ram into your shoulder and hurt your shoulder if you're not careful, actually. So there is a recoil. A more dramatic version of that, if you think back to like more in history, before they had like rifles and stuff, they had cannons. If you think of a cannon on a field, if you've seen movies where they had cannons, they shoot a heavy cannonball out, but that would cause the actual cannon, its barrel and everything, to move backwards. And if you're standing right behind the cannon, that's not a good idea. So that's called recoil, and it's due to Newton's third law. So the same thing happens here. Rayshon pushes Iverson, but because the surface is frictionless, Rayshon actually doesn't have anything to grip his shoes on. He's got nothing to brace himself with, so he's going to actually end up sliding backwards. And we'll calculate his acceleration moving backwards. So going back to Newton's second law, acceleration will be the force divided by the mass. And the force is 360 newtons west. This is the force on Rayshon. And Rayshon's mass is 90 kilograms. Your Rayshon, 90 kilograms. So Rayshon's acceleration is going to be 360 divided by 90. That's 4.0. Units of acceleration are meter per second squared. Direction will be west. Okay, so that's Rayshon's acceleration. And then D, what happens after the push is over? So when the push is over, the push is only going to last like less than a second probably. If you ever push someone, you normally just you shove them and it takes less than a second and that's it. But what's the aftermath of this? Well, because they're on a frictionless surface, there's nothing to stop them. Okay, so if you're just in the hallway of the school and you push someone, like they'll move backwards, but they'll stop because there's a floor with friction on it. But if you're on a frictionless surface, you're actually just gonna slide on forever. There's no friction to slow you down. And they will slide at constant velocity due to Newton's first law. They will just maintain their velocity. So they will slide in opposite directions. At constant velocity. So that's due to Newton's first law. I'll write N1 there to indicate that. Okay, gravity. Gravity has a formula. So you can calculate how strong the Earth is pulling down on an object or any other celestial body. Sometimes we do problems where it takes place on the moon or a different planet, and the number will be a bit different. But regardless, this is the formula on how to calculate how many newtons gravity is pulling down on an object. M is the mass of the object. The heavier the object is, the more gravity the Earth will pull down on it. And G is called the gravitational field strength. And that depends on what celestial body you're referring to. So if it's the Earth, the G value is 9.8 newtons per kilogram. But if you're on the moon, as some astronauts have been, it's a lot less. It's only 1.6 newtons per kilogram because the moon's a lot smaller than the Earth. If you're on Mars, which is something in between in terms of size, the Earth and the moon, the value there is 3.7 newtons per kilogram. A few things to point out that may be the difference between full marks and almost full marks when you're giving presentations and you're talking about this formula. G, as written here, the full name of G is called the gravitational field strength. It's not just gravity. Okay, so if you call G gravity, you're not going to get full marks. FG is gravity. Okay, the actual force is called gravity, but lowercase g, just like that, is called gravitational field strength. Okay, so for you perfectionists there who really want to get perfect on your presentations, you have to say the terms properly. The units here are newtons per kilogram. So Earth, for example, has a value of 9.8 newtons per kilogram. That means that a 1 kilogram object on Earth would feel 9.8 newtons of gravity. A 2 kilogram object on Earth would feel double that, 19.6 newtons of gravity. A 3 kilogram object would feel triple that, 29.4 newtons of gravity. Okay, so that's how you can understand the units of newtons per kilogram. The more kilograms it is, the more newtons of gravity you're going to feel. It turns out that a newton per kilogram is mathematically equivalent to a meter per second squared. So G is sometimes used to refer to the gravitational acceleration, because an object in free fall falls at 9.8 meters per second squared acceleration. it's the same number, 9.8, but it's different context. Okay, so if you're talking about accelerations, an object accelerating, you should stick with meters per second squared. But if you're talking about forces, you should be using newtons per kilogram. Okay, so depending on what situation you're in, choose the appropriate units. Even though mathematically they are equivalent, it's better if you stick to the proper context. Okay, the force of gravity is also called the weight of an object. Physicists use the word weight to represent how many newtons an object feels due to gravity. Okay, how many newtons an object feels due to gravity. So weight and mass end up being different things. Mass is how many kilograms an object is. That's determined by what stuff it's made out of. In other words, what all the atoms are that are put together to make the object. Those atoms each have a mass. You add them all up, you get the total mass of the object. Okay, so it's based on the atoms themselves, but weight is based on the force that the Earth or whatever object you're on is the force that is pulling on those atoms. So there is a difference between mass and weight. If I transport you to another planet, your mass will stay the same because the atoms you're made up out of are the same. However, your weight will be different because the other planet presumably will have a different amount of gravity pulling down on you. Okay, so we'll do some example problems. A, what is the weight of a 50 kilogram box on Earth? Okay, so the weight, some people use capital W for weight. Alternatively, as I said on a previous slide, weight is equal to the force of gravity. That's the definition of a weight. So you can use either of those two symbols. And what I'm trying to teach you now is that the weight of an object has a simple formula, m times g. So in this case, it's 50 kilograms times 9.8 newtons per kilogram, because it does say that we're on Earth. So we use the number 9.8. And that will make 490 newtons. And that should be the two significant digits. So I'll just underline the first two digits there. B, if this box is placed on a lift and is accelerated at 0.40 meters per second squared up, what is the lift force? Okay, so this is more complex, a lot more complex actually. So to do this, I'm going to draw a free body diagram to help me out. So this will be my box. What forces are acting on this box? Well, it's on an elevator. That's what a lift is an elevator. So the elevator is pulling it up, pushing it up. And that's going to be called the normal force. Okay, so if you're on an elevator, you're standing on a platform, and so it's offering you a normal force, pushing you up. There's also gravity pulling down on the box. Now, pay attention to how long I drew these arrows. I drew the upwards arrow larger than the downwards arrow because the object is accelerating upwards. If Newton's laws say that if an object is accelerating, the forces have to be unbalanced. And since it's accelerating upwards, the upwards force has to win. All right. So that's just a diagram to help. So with this, I can use my info from before. I know the force of gravity is 490 newtons. And I have to find out what this lift force is. I have to find out how many newtons that lift force is. So it's got to be bigger than 490. But how much bigger? So the idea here is for you to calculate the net force of the object on the object. F net equals ma. That's an equation you're going to have to be getting used to. So the mass is 50, and the acceleration is given as 0.40. So we multiply those together, and I get 20 newtons. So I know that the net force has to be 20 newtons. I also know that there's 490 newtons aiming downwards. So with some mental math, I can determine what my upward force has to be. It's going to have to be 510 newtons. It has to be. That's how you make a net force of 20. Okay, so my answer is 510 newtons to the tens column. And the direction is up. Yeah, don't want to forget the direction there. Going back to part A, my answer does not have a direction, actually. I guess I didn't emphasize this, but weight is a scalar. They only want the magnitude of the force of gravity when they ask you for the weight. So there's no direction in part A. Okay, C. If the lift continues raising the box, but now at a constant velocity, what is the lift force? So the key words here are constant velocity. And going back to Newton's first law, I really want you to emphasize that if an object is going at a constant velocity, the forces must be balanced. Forces must be balanced. The net force must add up to 0. So therefore, the lift force, it has to be exactly balancing out gravity. So it has to be exactly 490 newtons up. Okay, now part D. If the lift is raising the box and the velocity is 2 meters per second up, but then gradually slows down to a stop over the course of the next 3.0 seconds, what is the lift force during this slowdown? So this adds a level of complexity to the problem here. They're telling you an initial velocity of 2 meters per second up. They're telling you an elapsed time of 3 seconds. And they're telling you a final velocity, actually, because it comes down to a stop. So you should have some alarm bells going off that this is related all the way back to uniform acceleration formulas. In part B was a little complex. We had to do it in multiple steps. And we used the acceleration to help us define the net force. We're going to do the same thing in part D, but we have one extra step to do, which is we have to find the acceleration ourselves this time. They provide us the information to determine the acceleration ourselves. So let's do that first. I know my starting velocity is 2.0 meters per second up. I know my stopping velocity is 0 meters per second. And the elapsed time is 3 seconds. So the acceleration, it's actually the first formula of the kinematical formulas. If you look at the front of the class at the top, formula number 1 gives you a direct calculation of acceleration. So that will be uh, 0 minus 2.0 over 3.0, which gives negative 0.6 repeated Okay, repeated meters per second squared up. So negative 0.6 repeated meters per second squared up. I'm going to keep all of those infinite number of sixes in my calculator when I do the next step. You don't want to round too early. So we're going to keep all those sixes for now. Okay, so with that acceleration, I can find the net force. So the mass is 50 times the acceleration I just got, negative 0.6 repeated. So that makes negative 33.3 repeated. Newtons up. Or in other words, positive 33.3 repeated newtons down. So that's my net force. Drawing my free body diagram, I have a force of gravity of 490 newtons. I have a lift force, but this time my object is slowing down. Okay, the elevator is going up, but it's slowing down. So my lift force needs to actually be shorter than gravity. It needs to be less, okay, because gravity needs to win this time in order to successfully slow down the object. And I know my net force. I just calculated it. My net force is 33 newtons down. Okay, so what must the upwards force be? Essentially, it has to be 33 newtons less than 490. It's got to be 33 newtons less than 490. So my upwards force, my lift force, is going to be whatever 490 minus 33 is. So I think that's 457. I'm rounding to the nearest whole number here. But this should really just go to the tens column anyway, so those decimals don't matter too much. So 457 newtons up. Okay, so that is my answer. All right, lifting a bucket is very similar to the lift question we just did. So I think I'm going to skip this one for now to save time. Yeah, very, very similar to what was just done. The only difference is instead of calling it a lift force, we call it a tension. That's really the only difference, I think. But then there's lifting two buckets. Okay, so this is more complex. So I'm going to go over this one. A 2 kilogram bucket is tied to the bottom of a 3 kilogram bucket, as the diagram shows. The buckets are moving downwards, but slowing down at an acceleration of 1 meter per second squared up. Determine the tension in each rope. Okay, so when you have objects moving together, they are connected together and moving together. There are usually a number of strategies to apply in these situations of connected objects. One strategy is to look at the objects individually and try to do calculations of objects individually. And a second strategy is to combine the objects together and treat them as one big object. And depending on the situation, you can do one or the other. In this question, we can kind of do a little bit of both. So to find T1, so the rope at the very top, an effective, like the quickest thing to do is actually to just realize that that one rope is pulling up 5 kilograms, right? It's got to pull up 2 buckets. It's got to support both buckets. So that one rope is pulling up 5 kilograms. What's a good word here? Imagine, I guess. Reimagine the scenario as a rope pulling up 5.0 kilograms. That's the both masses added. Okay, so to do that, I will draw a free body diagram with a 5 kilogram object, and it's being pulled up by tension 1, and there's gravity resisting that. Now, how long do I draw gravity? Do I draw it the same size as tension 1, or longer, or shorter? Well, it's going to be shorter. It's going to be shorter, but why? If you say it's going to be shorter because it's moving upwards, that's not good enough. You need a more specific word than moving. Actually, it's not even moving upwards, it's moving downwards. So you'd be dead wrong if you said it's moving upwards. The key is acceleration. The key is always acceleration. The acceleration is upwards. Acceleration is upwards. Okay, so whatever direction the acceleration is, that's got to be the direction of the net force. So gravity has to be shorter than the upwards tension in this case. Okay, gravity can be computed with mg. So that will be 5 kilograms times 9.8. That's 49 newtons. So gravity is 49 newtons. So my answer, tension 1, is going to be something larger than 49 to be able to accelerate it upwards. How much larger? Well, then we calculate the net force again. So F net equals MA. So the mass is 5 kilograms. The acceleration is 1.0. So the answer there is 5.0 newtons up. Okay, my net force has to be 5 newtons up. So there's 49 newtons down. So that, I can do mental math there. It has to be 5 more than 49. So it has to be 54 newtons up. Okay, so that's how I figured out this is 54 newtons up. Now what about the other rope, the rope in between the 2 buckets? So when you have to calculate the force in between 2 objects, it's more of a wise strategy to separate the objects and to just think of individual objects. To find T2, I'll say it's simplest to just focused on one of the buckets. And it's your choice. You can focus on the 3 kilogram buckets or the 2 kilogram buckets. I think it ends up being easier to focus on the 2 kilogram bucket. So I will do that. I'm going to draw a free body diagram for the 2 kilogram bucket. I just drew it bigger so I can write 2 kilograms in it a bit more neatly. Okay, so what are the forces acting on a 2 kilogram bucket? Well, there's a rope pulling up on it, that's T2. Okay, only the second rope is directly attached to the 2 kilogram bucket. So that's the only tension you draw in your free body diagram. And then there's gravity pulling down on it. And again, this gravity has to be less strong than the tension pulling it up due to the acceleration of it being upwards. Okay, so this is going to work the exact same as above, just with the 2 kilogram object. So the force of gravity is mg. So that's 2 times 9.8. That's 19.6 newtons. Down. That's only good to the 2 sig fig, so I underlined the 1 and the 9. I'll get my net force again with F equals ma. So 2 kilograms times 1 meter per second squared equals to 2.0 newtons up. So my upwards force must be 2 newtons larger than 19.6. So that would be 21.6. And that's only good to 2 significant digits. All right, so there you have it. I can do a little check here, actually. I'll spend the time to do a little check. So I looked at 2 buckets together. I looked at just the 2 kilogram bucket by itself. Now I'm gonna look at the 3 kilogram bucket by itself and just do a little bit of a check. So with the 3 kilogram bucket, this is actually more complicated. There's actually 2 ropes attached to the 3 kilogram bucket. There is tension 2, which is pulling it downwards, actually. It's downwards because it's attached to the bottom of the bucket. There's gravity. I'm not quite sure how they compare, so I'm going to draw them. I think it's a little bit bigger, so I'll just do that. And then there is tension 1, pulling it up. So I'm actually, I've calculated both tensions. So tension 1, I calculated as 54 newtons. Tension 2, we calculated as 21.6 newtons. And then gravity, we're going to calculate with mg. So 3 kilograms times 9.8. That gives 29.4 newtons. And so if you add all these together, we have 54 going up. I'm going to take away 21.6 because it's pulling it down. And we're going to take away a further 29.4 from gravity pulling it down. And when I subtract those, I get 3. Yeah, I get 3. I get 3 newtons. Okay, so I got the net force just by doing the subtraction of the forces in the free body diagram. But it's supposed to also equal MA, right? Newton's second law. It's supposed to equal MA. So we'll check if this does the job. So the mass is 3. The acceleration is 1. 3 times 1 is 3. So I just did a little check to confirm that my answer actually makes sense when I just look at the 3 kilogram bucket by itself. Okay, so now I'm really, really confident that I got the right answers here.